Huh? Hey, there's something you don't see in a toilet every day. Anybody lose their glasses? Last chance. Woohoo! The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
That's a right triangle, you idiot! Go!
Hello class, welcome to today's lesson 3.4, which is a miscellanea of important trigonometry results. We're gonna look at maybe 5 or 6 results, and they may look as though they are disconnected more or less, and in some way they are disconnected. The only connection that they have in between is that they are related to trigonometry. But other than that, you may think that they are a little disconnected. Okay, let's go over these three in concepts today. Number one, the Pythagorean Theorem. I know that you know it, but we're going to prove it today in case some of you have not seen the proof. It's a very easy proof. Number two, the Pythagorean Identity for trigonometric functions. And number three, we're going to define tangent of theta as the ratio or the division of sine of theta over cosine of theta. And we're going to look at the equation of a line through the origin as y equals x times the tangent of theta. We're going to see what it means in a moment. So this is going to be another expression or another equation that represents a line. In this specific case, when it's through the origin. So let's start. Probably everything is gonna fit in here. So number one, the Pythagorean theorem, the demonstration. Okay, what does it say? Remember, it only works for right triangles, only for right triangles. And remember that right triangles are the ones that have an angle of 90 degrees, also known as a right angle. And usually we label its sides as A, B, and C. That's usual. It doesn't have to be like that. And the Pythagorean theorem says that there is a relationship between these sides, and that relationship is this one. That's the Pythagorean theorem. Okay, when you have this type of triangle, this relationship is satisfied. I want you to start using the names for these sides. Remember, when you're talking about a right triangle, this side and this side are called catheti. Let me write that down. Cathetus is the singular. For example, A is a cathetus, B is a cathetus, and A and B are catheti. A y B son catetos. Cathetus, singular, catheti, plural. There you go. And this is called the hypotenuse. And these words, hypotenuse, cathetus, and catheti, only work in the context of right triangles. You cannot use them in the context of any other type of triangle. Say you have this triangle, and this is not a right triangle. Okay, how do you know? Well, you're not seeing this mark or anything that tells you that this is a right triangle. And let's suppose this is an obtuse angle, about 150, let's say. So you cannot call any of these sides the hypotenuse. Even though this is the greatest side, you cannot call it the hypotenuse, or these two the catheti. No. What do you call them? Sides. That's it. Largest side and I don't know, another side and another side. That's it. You cannot call them this way. Okay, so now let's demonstrate the Pythagorean theorem. The proof goes as follows. Well, one of the proofs. There are about 500 plus demonstrations of this theorem, the most popular theorem in mathematics. Okay, first you're going to construct a square like that. This is supposed to be a square. Okay, and then what we are going to do is the following. Well, I don't need to, even though technically speaking, I should write these symbols in order to then denote that this is a square. Just by telling you that this is a square, that's enough, because I don't want to clutter the demonstration. So there you go. This is a square. What we're going to do next is this. We're going to divide each of these sides in the following way. In two unequal parts, like so. I'm going to call this little part A and this larger part B. And I'm going to do the same for all of them. I'm gonna part each of these sides in the same way, in part A and part B, but in this way. Like you're gonna go B, and then A, and then B, and then this is A, and then B, and then A, and then B, and then A again. Okay, like that. Okay, so you do this. Next, you can see that we have these four marks, this mark, this, and this. We're gonna join them. In this way. Okay, there you go. And what results is a square. This little thing here is also a square. How do you know that? How do you know that's a square? I'm gonna give you an exercise about that. Okay, that's the only thing I want you to prove, that this is in fact a square. Okay, so far what you observe is that this is a shape or a polygon of four sides. That doesn't mean it's a square. Okay, I can draw any other polygon of four sides. That doesn't mean this is a square. You see, how do you prove that this is in fact a square? That's going to be left as an exercise. It's not that difficult. And remember that the square is the figure of four sides with four right angles. This, and this should be right, and all the sides should be equal. So that's left as a demonstration. Okay, so we have this now. What's next? What we do is the following. I'm going to erase this part. I'm going to say that the area of the largest square, which is this one that I'm tracing, the area of the largest square, which is equal to, what are the sides? A plus B, right? All of this side is A plus B, or B plus A. Doesn't make any difference. So therefore, all the area of this largest square is equal to A plus B to the square, right? A plus B times A plus B, that's going to be the area of the whole square, the big square. So this is the area of the big square. Okay, fine. And that's going to be equal to the area of the following five figures, which is this triangle, this, we have four, and the area of this small square. Okay, so basically the areas, the independent areas of all of these five shapes has to be equal for geometry to the area of the largest square. So what is the area of this square? If we label these sides as C, okay, C, 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 and C, therefore the area of this small square, sorry, is going to be C squared. Do you agree? That's the area of this square. And next, all these triangles, as you can observe, are equal because both have height A and base B. Can you observe? All of them, height A and base B. If you rotate them in certain ways, you can always say that they are triangles with height A and base B. So therefore, basically, the area of these four triangles, the areas is 4 times the area of a single triangle, okay? And that's going to be base times height over 2. Base times height over 2. This is the area of a single triangle, and if we multiply by 4, we're taking into account all of them. So basically, one more time, the area of the whole square is equal to the area of the small square inside plus the areas of the 4 triangles inside. There you go. Okay, and then we have everything in order to calculate, or in order to find the Pythagorean theorem. All we need to do is this. We need to reduce this equation. Let's expand this binomial to the square. You're going to get the following, right? And then on the right side, we're going to get this. 4 times this fraction, we're going to get this, right? Okay, then we have this term on both sides of the equation, 2ab and 2ab, so they go away, they cancel one another, and my final result is that a squared plus b squared equals c squared. I'm gonna frame it because this is in fact my Pythagorean theorem. Look, what is a, what is b, and what is c? Look at this triangle in particular, this one. A and B are the catheti of the right triangle, and C is its hypotenuse. So the square of this catheti plus the square on this catheti is equal to the square on the hypotenuse. A squared plus B squared equals C squared, like you have in here. And that completes the proof. So there you go. This is one of the most common algebraic demonstrations of the Pythagorean theorem. There are way too many since antiquity. I mean, this theorem has been investigated since the Greek. Some people say that the Chinese also had this theorem even before the Greek people. So there are, that I know, there are over 500 different demonstrations of this theorem. 500 different demonstrations. That's unbelievable. I know only about 10 or something like that. So this is one of the proofs. I hope you have understood it. Do it on your own. You're gonna do it as an exercise. And so that's the demonstration of the most popular theorem in mathematics. Even people that know mathematics at all know about the Pythagorean theorem. Okay. So number 1, done. Number 2, the Pythagorean identity for trigonometric functions. What is this? The Pythagorean identity. Okay. This identity is the following. I'm going to write it down first. For any, well, let me write that context. For any angle theta, we have the following, that the squared sine of theta plus the squared cosine of theta equals 1. Okay, so there is a relationship also between the sine of the angle theta and its cosine. What is the relationship? That the square of the sine of theta plus the square of the cosine of theta is going to be equal to 1. And let me clarify again this notation, okay? Because I know that this looks weird, having the square on top of the sine. Okay, what this means, guys, is exactly the same. It's completely equivalent to this. Completely equivalent. Sine of theta to the square plus cosine of theta to the square equals 1. These two statements are the same. The most logical notation would be this, because this in fact cannot be misinterpreted, or it's not ambiguous. And this one, this one causes trouble for everyone starting to look into trigonometric functions. This is weird. Okay, you have to get used to this notation. Why did mathematicians decided upon this notation? I don't know, but it's the same as this, and they decided that in order to represent this in a much economic way, they were going to eliminate the parentheses and put the square on top of the sign. So again, one more time, this is completely equivalent to this. Completely equivalent. Okay? All right. Now, that's not to be confused with this. If you are shown something like this, okay, what this means is the sine of theta to the square. The square is being applied only to the angle, okay, not to the whole function. This is not the same as this. What this means is the sine of theta, all of that to the square. And what this means is the sine of theta to the square. Okay, only the square is being applied to the angle, and in here the square is applied to, like I said before, to all of this. Okay, so do not get confused with the placing of the square. It's gonna take you some time to get used to it. Just remember that it's not the same. It's not the same. And when you are in doubt, look it up. You have Google. Look it up in order to tell the difference between these two notations. Okay, so this is the Pythagorean identity. How do we prove it? How do we prove that that's true? Here it goes. Proof. I draw my Cartesian plane. I'm gonna draw any angle in standard position. I'm gonna draw, this is the initial side, and now I'm gonna draw the angle so that it ends in the third quadrant, because I always do it in the second quadrant, right? Or the first. Now I'm gonna go now into the third quadrant. This is the terminal side, and my angle is this one. I'm not gonna draw it for clarity in the diagram, but my angle is this one. Remember, always draw this little arrow which tells you the direction of the angle. It's rotating counterclockwise, but I'm not gonna draw it for simplicity. I'm just gonna imagine that it's there and that the angle is called theta. Okay, fine. Now, remember, in the context of the definition, the new definition of trigonometric functions, what we do is we find, once the angle is drawn in standard position, now we find any point on the terminal side of the angle. This point has coordinates x, y, and this point has a distance r from or with respect to the origin. So this is r. Okay, and we can always create this sort of triangle by drawing perpendiculars to some of the axes. In this case, I'm going to draw this perpendicular to the x-axis, and therefore this catheti is y. The length is y. Well, in absolute value, right? Just remember that. I could do this. This should be the proper way to do it. The absolute value of y, because what is y? Y is a negative number. Y is a negative number, and so is x. This x is a negative number. So if I write that this is equal to x, okay, the distance from here to here is x, or the catheti is equal to x, that would be technically wrong. It's in fact the absolute value of x and the absolute value of y. but this is gonna clutter my diagram, so I'm gonna just dispense of that. Just remember that we're talking about absolute values. This catheti has a magnitude of x in absolute value, and this catheti has an absolute value of y. Okay, so we have there our triangle with its catheti and its hypotenuse. Okay, fine. Now we remember the definition of the trigonometric functions for this angle theta. Now I can draw it. So the trigonometric functions are by definition the following: sine of theta equals y over r, cosine of theta is equal to x over r, and tangent of theta is equal to y over x. Okay, and remember what I want to prove this. Okay, so if I have these definitions, why don't we square this this equation? Square this side and this side. What are we gonna get? We're gonna get this. Sine squared of theta is equal to the square of this fraction, which is going to be equal to this. Okay? And I'm gonna do the same for this other equation. I'm gonna square the left side, and that's gonna give me the cosine squared of theta. And if I square the fraction, the left side, I'm gonna get x squared over r squared. And it's not important to square this one because this is not involved in this identity. So I have these two equations now. Okay, what do I do next? Well, I'm gonna actually add sine squared of theta plus cosine squared of theta. I'm gonna do it in here. Plus cosine squared of theta. And according to these equations, sine squared of theta is equal to this fraction, and cosine squared of theta is equal to this fraction. So I'm going to replace this with the corresponding fractions, which is sine squared of theta is equal to this, and cosine squared of theta is equal to this. So there you go. I end up with this equation. Fine. Now, what can I do next? I can do this. Sine squared of theta plus cosine squared of theta is equal to all of these two fractions, or the addition of these two fractions. They have equal denominator, so I can add them in this way. Right? Okay. And now you may be thinking, okay, how do I get the 1 on the left side? How is this equal to 1? If this is true, then therefore this should be true somehow. By some process, I should get that y squared plus x squared over r squared is equal to 1. And that process, in order to find that, is the following. It's just the application of the Pythagorean theorem to this triangle in here. Remember, this is a right triangle, catheti x and y, and hypotenuse r. So according to the Pythagorean theorem, I should have that x squared plus y squared is equal to r squared. You see? So basically, this is equal to r squared, and I can substitute in here. Sine squared of theta plus cosine squared of theta is equal to all of this, which is r squared over r squared, and that's it. We have completed the proof. Equals 1. There you go. So this is a demonstration that the Pythagorean identity, sine squared of theta plus cosine squared of theta, is equal to 1 always. So you may think that this is in fact like the Pythagorean theorem in the context of trigonometric functions. Okay, so it's called Pythagorean identity. Okay, fine. So that completes the proof. Oh no, it's here, and that's it. Okay, number 3. The definition of tangent of theta as this ratio. That's even simpler. Well, I'm going to erase the whole thing already. Okay, and number 3 was the definition of tangent of theta as sine of theta over cosine of theta. Okay, so one more time, very quickly, if I'm talking about some angle in standard position, let's draw it here now. This is theta, and then this is the point on the terminal side. This is r, and therefore, if I have this, all of this context, I can define the trigonometric functions of theta as sine of theta equals y over r, cosine of theta equals x over r, and tangent of theta as y over x. These are definitions. There is nothing to understand in here. It's a definition. A definition is not to be understood. It's just to be accepted. They may be useful, they may not be useful, but there is nothing to understand. Okay, these are not laws or theorems. It's a definition. I hope you understand what I just said. There's nothing to understand here. Okay, if the first person that created the mouse, okay, he gave it a name. He said, okay, this object is gonna be called the mouse. There is nothing to understand about that. Okay, he called it that way. It's a definition. Or the person that first created a chair. Okay, it's a definition. The word chair is a definition. Okay, it's an object to sit upon with 4 legs. That's it. That's the definition. There is nothing to understand. Like you never ask why. Why is a chair an object to sit upon with 4 legs? That's not a valid question. Okay, it's a definition. There is no reasoning to get to that definition. It's an act of creation, so to speak. Okay, so these are the definitions for the trigonometric functions of this angle. And as you can see, we can do the following. If I get to play with these things, you know, I can divide. If I want to, I can divide or make up the ratio of sine of theta over cosine of theta. I can go like this. Okay, let me divide them. And let's see what happens. Sine of theta over cosine of theta is equal to y over r over x over r. You see? And then we perform this division of fractions, and we're gonna get the following: y over x. Make sure about this. Okay? All right. So basically, sine of theta over cosine of theta is equal to y over x, which is equal to tangent of theta. There you go. So basically, we have demonstrated that the tangent of theta, the tangent of an angle theta, can be also written as the ratio or the division of sine of theta over cosine of theta, and that's always valid according to these definitions. This is true. And finally, the other thing that I wanted to explain to you today is a new form of a line, of the equation of a line. If we have our Cartesian plane and if we have a line through the origin, okay, it's gotta be through the origin, like so. Let me call it L. Remember that one of the equations for the line, one of the simplest equations, is this: y equals m times x plus b, and m and b meant the slope of this line, and b is the intersection with the y-axis. In this case, b is going to be equal to 0 because the intersection with the y-axis is 0. So we can write this: y equals m times x. Okay, fine. Now we're gonna arrive at a different representation of this equation by making use of the tangent of theta, where theta is the angle of the line. Remember that the angle of the line always starts in the positive x-axis and you rotate counterclockwise until you hit the line. Okay, fine. Now you look at this angle and choose any point in the line, like so. Let's give this point coordinates a comma b. Okay, and therefore we can write the tangent of theta, the tangent of this angle. What would that be equal to? That's going to be equal to a over b, according to this definition. One more time. In this case, they're called y and x because my coordinates, no, I'm sorry, I made a mistake. It's going to be b over a. It's b, which is this, is the rise over the run. In this case, it's called y and x because I decided to call this point x comma y, okay? But it's the same definition. So tangent of theta is equal to b over a. Fine, perfect. And but also, if you remember, this is in fact the slope of this line. If you remember, the slope of the line is equal to rise over run. What is the rise? As we go from this point to this point, the rise is b and the run is a. So there you go. These two things are the same, and so we can write this: y equals the slope, which is equal to this, but this is equal to tangent of theta. So basically, we can write this: y equals tangent of theta times x, which is usually written in the other way around, x times the tangent of theta. So this is another way in which we can write the equation of a line that goes through the origin and has an angle theta. Remember, the angle of a line is the one that you form by starting in the positive x-axis and rotating counterclockwise. If the line was in this way, this is L, therefore the angle is this one. Okay, so this is the new equation for a line in terms of the tangent of its angle. Okay guys, so that's about it for today's class. Let's go to the workbook and solve those exercises, and we're going to continue with this miscellanea of trigonometry results in the rest of this week before we go over some applications of trigonometry. So there you go. Thank you.